We need to find the smallest value of a, at least 2, such that this fraction becomes a perfect square for some prime p and some b, also at least 2. This problem combines Fermat's little theorem with the properties of perfect squares in a way that requires careful analysis. The conditions are clear. A must be at least 2, p must be prime, and b must be at least 2. We're looking for the smallest such a. Notice a key property here. By Fermat's little theorem, for any prime p, this expression is guaranteed to be an integer. The theorem tells us that p always divides a to the p power minus a. The real question is, when is that integer a perfect square? Let's start by getting rid of this fraction. Multiplying both sides by p gives us a cleaner equation to work with. The structure of the left side immediately suggests factoring. There's a common factor of a in both terms, and extracting it will reveal the underlying structure we need to analyze. This factored form gives us the structure we need. We have a multiplied by an expression involving powers, and this will be crucial for determining when perfect squares can emerge. Rather than testing values randomly, let's think systematically about the constraints this equation places on a. The natural starting point is to ask, could a be prime? This question requires a careful case analysis. So let's suppose a is prime and see where that leads us. When dealing with two primes, a and p, there are naturally two scenarios to consider. Either they're the same prime or they're different. Each case will teach us something different about the constraints. Let's start with the case where a and p are distinct primes. This is where things get interesting, because when two different primes interact in an equation like this, they often create unexpected constraints. So we can write this second factor as p times some integer k. This substitution is going to be crucial. It's like finding a hidden variable that will expose the contradiction we're heading toward. Now watch what happens when we substitute this back. The structure becomes much clearer, and we're about to see why this case is impossible. As expected, the p's cancel, leaving us with a much simpler relationship. But this simplicity is deceptive, as it's about to reveal a fundamental impossibility. This simplifies to a times k equals b squared. Here's where being prime becomes crucial. Since a is prime and divides this product, it must divide b itself. It's like a prime number's signature. It can't divide a product without dividing one of the factors. So b must be a multiple of a. Substituting this relationship creates a useful symmetry. The equation becomes symmetric with a squared appearing naturally. This kind of symmetry often signals we're approaching a contradiction. Dividing through by a gives us this clean relationship. The key takeaway is that a must divide k. Remember this. It's going to clash spectacularly with what we discover next. But wait, let's not forget what k actually is. It's this specific expression involving a raised to a power. And here's where the contradiction emerges. Think about what happens when we raise a to any positive power, and then look at it modulo a. It's always 0. So when we subtract 1, we get -1 modulo a. This is a fundamental property that's about to create our contradiction. Following this logic, k cannot be 0 modulo a. But we just proved that a divides k, which means k should be 0 modulo a. Do you see the contradiction brewing? We've walked into a mathematical impossibility. And there's our contradiction. We've proven that a both divides and doesn't divide k simultaneously. This logical impossibility tells us that our assumption was wrong. A and p cannot both be distinct primes. So that rules out distinct primes. But what if we let a and p be the same prime? This might seem like it avoids our contradiction, but as we'll see, it leads to an even stronger impossibility. When we set p equal to a in our original equation, the expression simplifies dramatically, and we're left with this much cleaner form to analyze. This simplification gives us a clearer structure to analyze. We're looking for when this expression involving a raised to its own power becomes a perfect square. The algebraic structure will be crucial. Now here's a classic move in number theory. When you see an equation like this, you want to rearrange it to reveal patterns. I'm thinking difference of squares, one of the most powerful factoring techniques in mathematics. We've set up a difference of squares, Notice the crucial condition. This only works when the exponent is even. For odd primes, a minus 1 is always even, which makes the factorization valid. Since we're assuming a is an odd prime, a minus 1 is even, which means we can take that square root. This is where the factorization becomes not just possible, but inevitable. This can be factored as a difference of squares. Now we have two factors whose product is exactly 1. In the integers, this is a very restrictive condition that severely limits our possibilities. Let's call this large expression a for simplicity. With this substitution, our equation becomes much cleaner to work with, and the constraint becomes more obvious. Here's the key insight. If two integers multiply to give 1, they must both be 1, or both be negative 1. But look at our factors. A is huge compared to b, so both factors are clearly positive. This forces both to equal 1. So we need both factors to equal 1. But watch what happens when we solve this system. It's going to lead to something absurd. Adding these equations reveals the contradiction. We get a equals 1, but a equals the variable a raised to the power of a minus 1 divided by 2. For any prime a that's 3 or larger, this expression is enormous, definitely not 1. This gives us our contradiction. Think about it. We're claiming that a prime raised to half its predecessor equals 1. For a equals 3, that's 3 to the first power. For a equals 5, that's 5 squared. These are never 1. But wait, what about a equals 2? It's the only even prime, so our factorization approach breaks down. The exponent becomes odd, so no difference of squares. Let's check this case directly. When we plug in a equals 2, we get b equals 1. But remember our constraint. B must be at least 2, so even the smallest prime fails. This completes our proof that a cannot be prime. Our case analysis has yielded a clear result. A cannot be prime. We've systematically eliminated every possible prime value for a through distinct contradictions. This means a must be composite, which is where we focus our search. Now for the systematic hunt through composite numbers. Rather than randomly trying values, let's be strategic. The smallest prime is 2, so let's see what happens when we fix p at 2 and vary a. When p is 2, our equation reduces to this triangular number formula. We're looking for triangular numbers that are perfect squares, a well-studied problem in number theory. Let's systematically check the first several values. Computing these triangular numbers, we see that none from a equals 2 through 8 give us perfect squares where b is at least 2. Each fails the perfect square test. For odd primes p, the analysis splits naturally into two cases based on whether p divides a or not. Each case has its own mathematical flavor and leads to different types of constraints. When p divides a, we only need to check the prime factors of a itself. This gives us a finite, manageable list to check for each composite number. It's like having a built-in shortcut. When p doesn't divide a, the mathematics becomes more sophisticated. The structure of a itself, whether it's a perfect square, has repeated prime factors or other properties, creates powerful constraints that often lead to contradictions. Combining these theoretical insights with careful computation, we can systematically rule out every value from 2 through 8. It's like a mathematical sieve, filtering out impossibilities until only the truth remains. After eliminating everything smaller, we arrive at 9, the first perfect square composite number. There's something poetic about this being our answer. Let's see if it works. The question is, can we find a prime p that transforms this expression into a perfect square? Given all our failed attempts so far, this is the decisive test. Let's start with the most fundamental prime, 2. If 9 is going to work, it seems natural to try the building block of the entire system. Substituting p equals 2 and computing 9 squared, we get 81 minus 9 over 2. This simplifies to 72 divided by 2, which equals 36, and 36 is 6 squared. After systematically eliminating all smaller possibilities, we found our solution. This is a perfect square with b equal to 6, which satisfies our constraint that b must be at least 2. We've found our complete solution. A equals 9, P equals 2, and B equals 6. All the conditions of our original problem are satisfied. Let's step back and appreciate what we've discovered. This problem took us on a journey through the deep connections between primes, perfect squares, and modular arithmetic. Our solution is elegant in its simplicity. A equals 9, P equals 2, B equals 6. Three small numbers that together satisfy this intricate mathematical relationship. The journey to this answer required us to eliminate every smaller possibility through a combination of theoretical insights and systematic computation. Each eliminated case taught us something about the structure of the problem. So our final answer is 9, the smallest natural number A that satisfies the given equation. What started as a problem about fractions and perfect squares led us through fundamental concepts in number theory, demonstrating the deep connections within mathematics. Thanks for joining me on this mathematical journey. If you enjoyed exploring this number theory problem, please like this video and subscribe for more deep dives into the beautiful world of mathematics.